The Dirac delta function is a function that is very useful for dealing with theoretical approximations and other weird situations. A really useful application of this is if we're considering the density of a point particle. If we draw the density of a point particle, where this is the distance from the center and this is the density, at any point that is not the absolute center, the value of this density is 0 because it's a point particle. And then what happens at the center itself? Who knows? But we do know that the integral of the density over, let's just make it one-dimensional here, the radius has to be the mass of the particle, right? And if our density is only non-zero at the exact location of the particle, r equals 0, then we must have an infinite density here. It's really hard to deal with situations like that. Enter the delta function. The delta function is defined as a function that has a 0 value everywhere except the origin and an infinite value right at the origin. And by definition, this is the symbol for the delta function, the integral over all of space is defined as 1. So the area under this infinitely tall spike is 1. A way that makes more sense to think of the delta function is as the limit of a series. So if we take the series of functions, starting with a function that spans from -1 to +1 and has a maximum height of 1/2, the area under this curve is 1. Now, if we consider our next function, which goes from -1/2 to +1/2 and has a max height of 1, the area of that function is still 1. If we take one that goes from -1/4 to +1/4 and has a maximum height of 2, it still has an area of 1. And so on and so forth, getting narrower and narrower. The limit of that series has a width of 0, a height of infinity, and it still has an area of 1. So that is the delta function. The first important property of the delta function is that if we take some other function, f of x, whatever it is, and multiply it by the delta function, the only place that that product will have a value at all is at x equals 0. So the product itself is equal to the function's value at 0 times the delta function. Now, if we integrate both sides, we notice that f of 0 is a constant, so we can pull it out. And by definition, the value of that integral is 1. So, sorry, I just wrote on my drawing there. So that's just equal to the function's value at 0. So any normal function times the delta function integrated over all space is just that function at 0. If we're interested in the function somewhere that's not 0, the delta function at x minus a will be centered at a. So it follows that the integral over all space of f of x times the delta function of x minus a will just be equal to f of a. So it essentially picks out the value of a function at some point. And the delta function, of course, can also exist in 3 dimensions, which is usually written as d cubed of r, where r is just the position vector. And the same rules apply. So it can also be used in 3 dimensions, like so. I'll just write it out. The integral over all space of some function of position times the 3-dimensional delta function of the position minus some point A is just equal to the function's value at that point A. So this is incredibly useful for point particles, especially when we're talking about electricity